The idea of the vehicles on magnetic cushion has been one of the most important ideas in improving transportation. Such a vehicle has been done in a laboratory at the Polytechnical Institute of Timișoara, Romania, in the 80s. You can see the laboratory of electrical machines. It was a team of professors, PhD students, and even undergraduate students. This team has been working years to compare different solutions and to come up with some original ones. And in finding these new solutions, a lot of experimentation was necessary. Most of the electronics components and systems have been produced at the university, but the mechanical parts have been produced, many of them, including the motors, at Electropower Works Craiova, who financed the whole project. The Romanian maglev, called Magnibus, uses a simpler configuration, but it is with a passive guideway and a linear homopolar synchronous motor, integrated propulsion and levitation control. Guidance is done separately. Here you can see the prototype vehicles, which weighs 4 tons and which flies with some noise, electromagnetic noise, along the 150-meter long track at the Polytechnic University of Timișoara, Romania. The heart of this vehicle is the linear homopolar synchronous motor. So we have linear motors, we have no wheels, and the linear motor is obtained from the rotary motor by cutting it along a generatrice and then folding it in a plane. And we can make a replica of any kind of rotary motor in a linear motor. This one, as you can see, is a linear induction motor, but we have used a linear homopolar synchronous motor with both DC and AC windings on board the vehicle. This is a double-sided linear motor, good for guidance. So as I said, Magnibus uses linear homopolar synchronous motors. This is the motor, AC windings, and below them are 2 DC coils. Levitation is controlled basically by the control of the DC current in the motor excitation, while propulsion and braking is done through the interaction between this AC winding control and the DC field. The Magnibus can have more than 4 motors. This one has 4 motors, 1 in each corner. It's a kind of bogie, a single bogie vehicle. It flies over the track or below the track at an air gap average of 10 millimeters. It could be up to 15 millimeters. The suspension of the vehicle dynamically at 10 millimeters is done through the state feedback or sliding mode control or other non-linear control of the DC current in the DC excitation of the linear homopolar synchronous motors on board. So we need a DC-DC converter, at least 2 quadrants for this. We need to measure or estimate the vertical distance between the motor and the track, the acceleration, and some kind of decoupling of the motion of the Magnibus. Magnibus is a kind of helicopter. First you lift it and then you propulse it or brake it. Lifting is done from 20 millimeters to the rated air gap of 10 millimeters. Levitation is unstable dynamically and statically, so the control is a very, very tough problem. The Magnibus use both AC and DC collectors, but with today's pulse width modulated IGBT converters, only DC is required for town applications. The passive guideway of the Magnibus, it's the extraordinary feature of this. It is very simple. It uses solid iron segments for levitation and propulsion and a solid slab for the guidance electromagnets. The propulsion and levitation and guidance systems are characterized by the presence of this linear homopolar synchronous motor, which is characterized by an efficiency above 0.8 while providing both levitation and propulsion, and by a power factor above or around 0.8, which is much higher than any existing maglevs. The power factor is crucial in rating the static power converter, whose weight and cost is reduced, and so is for the other parts of the equipment which depend on the apparent power. We experimented it here at the university on a 150-meter long track in 1985, 1986. We want to see if the most important parts are working. We had 4 synchronous motors in parallel. We had decentralized control with sliding mode for levitation, but some decoupling has to be done, and this can be done now with the technologies available in digital control. We managed to produce levitation with about 2.5 kilowatt per ton and 3.5 kilovolt amps per ton dynamically, which is quite good. While the efficiency was 0.8 at 10 meters per second, and the power factor was about 0.8. As you can see in these images, in 1980s, electronics was different from today. But even today, such things are still done before you find a good solutions, then you pack up. Now we have better computers than that. We have very good power collection up to 400 kilometers an hour. So we can dream of many, many applications of maglevs with better performance. And among them, Magnibus stands out as a very practical solution, which is waiting to be taken and used by people.